Today, in economic science, the mathematical model comes to the fore as an effective tool for researching and predicting the development of economic processes and phenomena. A special place among the economic mathematical models is the transport problem. The application of this task is making managerial decisions gives the opportunity to rationally distribute the funds and time of the enterprise, which has a positive impact on its development. Under the name transport problem, a wide range of problems is combined with a single mathematical model. Classic transport problem, the problem of the most economical plan of transportation of homogeneous product or interchangeable products from the points of production to the points of consumption, is most often found in practical applications of linear programming. It should be noted that many problems in their mathematical formulation are reduced to a transport problem. Thus, with this method you can find the optimal organization of work in the planning of construction sites, the distributions of given volume of work between different people, the delivery of goods and more. Finding the optimal solution to a transport problem can find application in different areas. In economic, in logistics planning, in the educational process, when developing databases, and in programming. Such a wide range of applications testifies to the relevance of the subject under study task. The rapid expansion of the spheres of application of the methods of mathematical modeling and optimization, which has been happening in recent years, creates the need for solving new classes of problems of increased complexity and dimension. The application of a parallel algorithm for finding a solution to a transport problem will be the best choice. The main advantage of parallel algorithms over sequential ones is the speed of execution. Therefore, the purpose of this article is to parallelize the algorithm of finding the optimal solution of a transport problem by the potential method by using OpenMP parallel programming technology. The transport problem is a linear programming problem that is used to determine the most economical plan for transportation of homogeneous products from suppliers to consumers. Here X is the volume of production, C is the rate of delivery of products from the I, supplier, to the J, consumer, B are the needs of consumer for products, and A is the inventory of products from supplier. There are two steps to solving a transport problem. The first step is building a reference plan. The most common methods of building the reference plan are method of the northwest corner, the least cost method, and the Vogel method. The next step is searching for the optimal plan. The most common methods of building the optimal plan are the Hungarian method and the potential method. When solving a transport problem, you must have an initial reference plan. The work of finding this plan was implemented using the least cost method. According to the method of least cost, the cells with the least cost of transporting a unit of cargo from the supplier to the consumer are selected first. Then we have to construct an initial plan. After constructing the initial plan, each of the methods in the table must be filled in m plus n minus 1 by cells, where m the number of suppliers, n the number of consumers. If the number of cells filled is less, then it is necessary to fill it an appropriate number of empty cells, recording in them zero transportation, and to consider these cells basic. However, when the number of cells filled exceeds m plus n minus 1, the initial reference plan is not properly constructed and is not the reference one. We already know the methods of finding the initial support plan of a transport problem, but we don't know if these basic plans are optimal. The reference plan is tested for potential optimality. According to each supplier, we put the potential U, and to each consumer, V. The reference plan potentials are determined from the system equations U plus V equal to C that write down for each filled cell of the transport task table. Using the calculated potentials, we check the optimality conditions U plus V less than or equal to C for unfilled cells in the table. If this condition is not met for at least one non-core cell, that is U plus V bigger than C, the current plan is not optimal and you need to move to a new reference plan. The transition from one reference plan to another is performed by filling a non-core cell for which the optimality condition is violated. A recalculating cycle is built for the selected empty cell. To each vertex of the cycle is assigned a specific sign, with an unfilled cell assigned plus, and all other alternately signs minus and plus. Enter into the empty cell the list of the numbers in cell with the sign minus. As a result of this redistribution of products, we will receive a new reference plan for the transport problem, which we again test for optimality. If the solution is optimal, then we calculate the minimum value of the objective function, the minimum cost of transporting the entire road. And if not optimal, then again build the recalculation cycle and move to the new reference plan using the cycle shift. The process is repeated until the optimal solution to the transport problem is obtained. The program is designed using C++. C++ compiled applications are mobile, namely it can be run on computers from different manufacturers and operating system, making C++ particularly popular. This allows you to edit the number of rows and columns of the matrix, add or delete them, fill in the data manually through the application interface, or read from a file. In the absence of redundancy, no intermediate results are output, only a post-degeneration reference plan, U and V potentials, a free cell estimation matrix, an optimal plan at minimal transportation costs. Also, we output all the intermediate and final results in a text file. In it you can see the dimension of the matrix, the initial matrix, all stages of its modification and such end results as the execution time, the reference plan, and the minimum costs. In this work we propose an algorithm for finding the optimal solution of a transport problem that can be used on multi-core systems. The latter are increasingly used in various subject areas and are a better opportunity to increase the power of processors. The parallelization was done using OpenMP parallel programming technology. The efficiency of this algorithm is tested by running it on dual and quad-core processors. The validity of the results obtained in the article is confirmed by the theoretically obtained estimates by Amdahl's law. You can also conclude that this algorithm allows you to get the best solution for the transport problem for large dimensions of input with greater efficiency. This study is particularly relevant in the current rapid development of multi-core systems.